In this example, we're going to prove the Manhattan norm is actually a norm. Okay, so the Manhattan norm, the one norm, is equal to the sum of the absolute value of the components. And a norm satisfies three properties: positive and definite, okay, which means that the one norm for x is greater than or equal to 0, and that the one norm for x is equal to 0 only when x is a 0 vector. Next, we have to satisfy homogeneity. So the absolute, or the one norm of alpha x for any real number alpha equals absolute value of alpha times the norm of x, again for a vector x. And third, the triangle inequality. So that the one norm of x plus y is less or equal to the one norm of x plus the one norm of y. So we need those three properties to hold. Okay. So here we're going to take x to be some sort of vector x1, x2, all the way to xn. And so for positive definite, since each component xi by absolute value is greater than or equal to 0, we know that the sum of those guys has to be greater or equal to 0, which means that for any vector x, the one norm, which is just the sum of these xi's, is greater or equal to 0. Okay, but we know a little bit more than that. And we know that since the sum of the xi's are greater than or equal to 0, that the norm is equal to 0 if and only if each of the absolute xi's is equal to 0, because none of them can get negative. Okay, and so since this is greater than 0, we know that it equals 0 only when all of these x's, these xi's are 0, which means that our x would equal the 0 vector. Homogeneity. Well, if we take a real number alpha, the one norm of alpha x I should just be a little careful here. The one norm of alpha x is equal to the sum of the absolute value of alpha times each component xi. Now, the component times some scalar, the absolute value of that is that scalar by absolute value times each component. But of course this, because each value here is being multiplied by the same scalar, it's absolute alpha times the sum of the absolute xi's, and the sum of the absolute xi's is just the norm. And so the one norm of alpha times x is equal to the absolute value of alpha times the one norm of x. And finally, the triangle inequality. Well, if we take vectors x and y, the one norm of x plus y is equal to the sum of the absolute value of xi plus yi. So each component added up. Now that, by the triangle inequality for numbers, is less than or equal to the absolute value of xi plus the absolute value for yi. This is then equal to the sum of the absolute value of xi's plus the sum of the absolute value of the yi's. The sum of the absolute value of the xi's is the one norm for x. And this is the one norm for y's. And so since all three properties are satisfied, the one norm is indeed a norm.